Hi Relevance, this is Mr. Lim here, and this is our first video on calculations, balancing equations. Lots of fun. Alright, so we're going to learn how to balance an equation. That makes sense. Right, so why do we balance equations? We're counting the number of particles and atoms in a substance because we want to accurately react two substances together. Knowing how many particles we will have allows us to react the correct number of particles and use all of our resources effectively as possible, because this is all about making the monies as effectively as possible. All right, so to work out how much of one substance reacts with another, we can look at the reactant and product formulas. Yeah, we knew that. Make sure the total number of atoms of each element is balanced, blah, blah, blah. All right, so hopefully we're getting better at this, but we're just going to go through some tips on how to do this better. All right, so tips of balancing equations: balance elements that are on their own in the reactant or product, like H2 or an O2. We do that last. Okay, so in this example here, we've got the O2, which is all by itself, and we're going to do that one last. So let's go through this. Okay, let's balance out the C first. We got 4. Let's balance out the H. We got 5. Okay, then balance out the O's. All right, well, we got 5 here, 5 here in the H2O. What's that? 8 there in the O2, which makes 13. You can't possibly make 13 with this, so what we're going to do is we're going to have to double both of these and maybe put a coefficient in front of this one. 2, 8, 10, and now we have an even number for that O2. Right, so we can say that there's 10 in the H2O, 16 in the CO2, so that makes, 26, which means that we can have 13 O2s, and that's the easy one to balance out at the end. All right, so balance the elements that are on their own in a reactant or product, like H2 or O2, last is the first tip. All right. Another tip is that you can treat most polyatomic ions, that's ions that are made up of multiple parts, like NO3 and PO4, right, as if one unit, and they stay if they stay as ions during their reactions. Okay, so you can see that this PO4 stayed as PO4, which means that we can treat it as one thing. That NO3 stayed as NO3 there, so we can treat that as one thing. So when we start thinking about balancing this, all right, this Ca3PO4 here, all right, we can see that there's 2 PO4s here and there's only 1 PO4 there, so I'm going to have to balance that out by putting a 2 in front of that one there. All right, if I put a 2 in front of that one there, I've got 6 sodiums there, so I'm going to put a 6 in front of this one. If I have 6 over there, then I'm going to need to have, well, I've got 6 NO3s, so I now have 6 NO3s, and that's how many I've only got 2 there, so I'm going to need a 3 over here, and that balances out the calciums as well. All right, so the calciums, the 3 there, match the 3 there, and so now I'm all balanced. So polyatomic ions, don't split them apart, because then you'd have to count out the oxygens here and the oxygens there. There's no point doing that. Just recognize that they all stay together, and then you can balance them a bit easier. Right. This one's really, really helpful, so we'll highlight some. Know the ratios between certain coefficients. So when you change one coefficient, you know what the other will change to. All right, so this was very similar to the very first question. Let's go through this. What we're talking about here is that, okay, see how C, the only place that C is in the reactants is in the C6H14, which means that the ratio of this coefficient for this C6H14, and because there's only one carbon on this side, the ratio of coefficients from here to here has to be some sort of 1 to 6 ratio, right? The 1 to 6 ratio. Also, the ratio of hydrogens here to here, right? There are 14 here, there are 2 here. Whatever numbers I put in front, there has to be a ratio of 1 to 7 to that H2, right? So those are some kinds of ideas there, but also recognizing that this O2 means that there has to be an even number of oxygens on either side, because you can't have an uneven number of oxygens with any coefficient on this one here, right? So they're going to be like either 2, 4, 6, 8, so on and so forth. Then you should recognize then that because this H2O here has only one oxygen, and the carbon dioxide is two oxygens, this here is going to contribute an even number of oxygens. This 2 here has to contribute also an even number of oxygens, right? Because you can't have an odd number of oxygens, otherwise you would not be able to balance it on this side. So having an even number of oxygens here means that this not only has to be a factor of 7, but also, a multiple of 7, but it also has to be a multiple of 2, right? So whatever this is, right, this number has to be even, and this number will have to be, well, this number can be anything that you want, right? But that number has to be even. So if I say that this the H2O has to have a 7 or of some sort in front of it, and it has to be an even, a multiple of 7 with an even number would make it, the lowest one would be a 14, so we'll try from there. Okay, if I have 14 there, I'm going to need a 2 here, so I'm going to put the 2 coefficient in front here. Okay, where's my colors? We'll put a 2 in front there. If I have a 2 in front there, I know that I have to have a 12 over here because I had a 1 to 6 ratio there, 1 to 7 ratio there. All right, and then I can work out how many oxygens I have. I have, well, 24 from the CO2, and I have 14 from the H2O. So 24 plus 14 is 38, which means that I need, what's that? 19? Yeah, 19 or so of these O2s. Okay, all right, and those numbers can't be simplified, so that means it's correct. All right, let's move on. Another tip is practice lots, but work out your own tips for balancing faster, because the count and balance each element is simple but too slow. All right, so generally, in year 9 and 10, we give you simple chemical equations, and so therefore, by counting out each atom there is, that's okay. But when we get to bigger ones later on, you are going to have to just think about those ratios and be able to do them quite quickly. And so you need to practice. All right, so something like this. Okay, this first one, I got 8 here, which means I need a 8 coefficient in front of this one at least. So let's try that as an 8. Right, that means I'll have 16 O2s, which means that I will need a 8 over here as well. And now that's all balanced. All right. This one here, I'm going to make sure that I think about this NO3 as a single unit and the OH as a single unit as well. So I know that this is going to be some sort of 1 to 3 ratio. So let's try this as a 3 here. If I have a 3 there, I'll need a 3 here. And that means that will actually help me balance out the OHs, because I need 3 of them there. And that's all balanced now. All right. Yeah, that's all balanced. Yeah, that's all balanced. All right, so that's how quick it can be. All right, then let's have a look at this last one. Again, we're going to take this polyatomic ion there and check that, yep, it's still a polyatomic ion there. You should also recognize that CO3s always split into the CO2 and the oxygen there make up that CO3, right? Which means that you need one H2O for every CO2, right? So therefore, let's have a look at this balanced out. I'm going to have to put a 2 over here because I want to match the PO4s, right? If I have a 2 over there, that means I have to have a 3 over here for the H2O, right? Because the ratio of the H's must be 2 to 3 ratio because of the coefficients there, right? If I got 3 of those, I'm going to have 3 of these, because you need to have 1 of each of those because of the way the CO3 breaks apart, and therefore I'm going to need 3 of those CaCO3s because that also balances out the calciums as well. All right, so that's how you can quickly balance out various things, but you got to practice lots. All right, adios.